Hello, and welcome to Reproducible Research in R. This is the first of a series of tutorials taught as part of a course that I'm developing for upper level undergraduates and beginning graduate students at Louisiana State University. I'm a professor in biological sciences at LSU. The course is sort of designed to explore the problem of reproducibility in mainly the biological sciences, but sort of throughout. And many of the people sort of enrolled in the course are in natural resources, are sort of scattered throughout other departments, including veterinary medicine, etc. So I'm looking forward to this. I think it'll be fun. And this lecture should be on YouTube as well. So hopefully anybody who wants to follow along can. And this is sort of the intro lecture. And so it's probably not going to gain nearly as many views as other specific lectures that go into things like how to use Git, how to use GitHub, how to do data manipulation and plotting in R. However, it's sort of nice to lay out sort of my expectations of what I want to see in this course, what I want students to learn out of this course, and how we will go about doing reproducible research for this course and hopefully beyond. And so how the course is structured for people who are at Louisiana State University is it will consist of one YouTube available lecture for everybody that will be quite general. And then the other lecture per week will focus on a paper discussion, and we'll also focus on diving deeper into some of the lecture material that maybe has more nuance or just needs this sort of deeper dive. And so the reading for this week is called A Manifesto for Reproducible Science, and it's in Nature Human Behavior. It was published in 2017, and it sort of lays out why we need to think about reproducibility when we design our experiments, when we collect our data, and just throughout the sort of scientific process, without going too much into the actual underlying philosophy of science. And so I'll take this time to sort of first go into the structure of the course via the syllabus. And so all of the course materials will be available or are available on GitHub. And I will share the link in the description of this video. Any users that are not a part of LSU are still more than free sort of to complete assignments, I believe. I'll share the links for those. As well as follow along with lecture notes and these video lectures. And so I sort of welcome you to do that if you've made your way and found this on the internet. So first I'm going to go over the syllabus as I see it structured, and then I'll go over sort of my expectations of the course, and then start to get into a little bit of the logistics of how I will teach this course, in addition to going over the structure of Markdown as a markup language. And so I will go ahead and share my screen now. Maybe I will share my screen. It's on a different screen. I am using Awesome Windows Manager on multiple screens, and it sometimes does not recognize it when I'm trying to get it to. And there we go. So I'm sharing the screen, and hopefully all you're seeing is a Emacs screen on the left and the compiled PDF on the right. And so this is the first lecture for the course in both uncompiled format, which it's written in Markdown, and on the right as a PDF. And so we will focus on the right in the PDF just because it's a little bit easier to read, but feel free to sort of compare visually the structure of them, because as we'll go over later, Markdown is actually a really clear markup language, which is incredibly useful because it sort of is used throughout. It's not just like this esoteric language or markup language that nobody uses. Github uses it in their own little flavor, like so you can use GitHub flavored Markdown. If you use Slack, a lot of commands that work in Markdown also work in Slack. And sort of it's very, very helpful to sort of know the structure of it throughout. And so here are the lecture notes, and I will pull up the syllabus for the course. And so I am hopping, and I think it's actually going with the hop. And so this is how the repository is structured for this course. And I'll move this to that window, and hopefully now you see the syllabus on the left. So I'm sorry for the structure of this. I know that it's sometimes difficult to see other people's setups and computer screens because I know my hotkeys and I know the sort of way that makes me most productive, which is a Linux environment and a sort of tiling web manager on top of it. And so hopefully that won't throw anybody off. Let me know if it does, and I can switch to sort of a classic non-tiling web manager, Windows manager, sorry. And so here is the syllabus on the left. This is a Tuesday, Thursday course. Sadly not taught face-to-face, but with the current pandemic, it seems both prudent and just a natural course of action to teach this as an online course. So hopefully by the time, so it's now July 2nd or 3rd, and hopefully by the time that this actually becomes released, LSU will sort of decide that online courses are the way to go, because face-to-face meetings don't seem very prudent this time. So the idea underlying the course, like why do reproducible research? And sort of the blurb that I wrote in the syllabus, I don't know if it fully encapsulates my opinion on why do reproducible research. But I think if we just think back, especially to the origins of biological science and ecology in particular, emerged out of natural science, natural history, a lot of very observational studies that were very potentially small sample sizes and things like that, where we couldn't necessarily take them as complete fact. And so lots of conceptual theory developed on incomplete ideas could lead to going down erroneous paths in science. And so the idea that I tried to lay out in the syllabus is that scientific knowledge builds on existing scientific knowledge. The generation of that knowledge comes from observation experimentation. And that knowledge is not without flaw. And so things like sampling bias, detection bias, are just publication bias, are constant specters in science in general, and especially in sort of biological science. And so that results in this corpus of scientific publications that seem almost quasi-independent, even though scientific knowledge should build on itself. And so this is related, and I won't go too much into how reproducible research fits into open science in general, but it builds into open science. And so with the sort of advent of the scientist not only being an observer of a natural system or an observer of some phenomenon, I think a scientist is also now becoming sort of adept at computer science, at becoming adept at developing code. In addition, wide-scale availability of data and different streams of data and the combination thereof is really, really important to progressing science. And so we see this in synthesis centers being developed, such as the one IDIV in Germany, or NCs in California, which is now defunct, SysInc. And so if you Google all of these, NCs, NCEAS, IDIV is IDIV, and then SysInc is SES. Y, N, C. And there's tons of others, sort of the NEON initiative, which is the National Ecological Observation Network, is another example of broad-scale monitoring of natural systems and then this synthesis of knowledge across different studies. And that synthesis sort of requires open access to data. And without open access to data, and that fits in the open science paradigm, you wouldn't have the ability to have reproducible research. And so what reproducible research means is the ability of someone who hasn't done the experiment necessarily to be provided with the raw materials, the data and the code, which to create the sort of final product, and their ability to run through and reproduce the results of that experiment. And that it sounds very simple, and it is not necessarily that simple. We can imagine many of us are old enough, ever so slightly, to have experienced sort of days when statistical analyses were sort of done in Excel or done in SPSS, or a language that didn't provide a programmatic interface, where you didn't actually give it code, you clicked on things in order to perform different analyses. And that's not reproducible, right? Just like fundamentally, if the software changes, or the ability changes, or the clicks change, the output changes, and the output shouldn't change. Fundamentally, in order to be reproducible, any researcher across any operating system, across any availability of scientific information, like sort of independent of the data and code, should be able to reproduce those results that you have found, or that any researcher has found and published. So I'll get off that soapbox for a little bit. We'll go into more detail about that when we talk about the paper in paper discussion, as far as what is reproducible research and what does it mean, and why does it matter to do reproducible research. So let's just accept that reproducible research is a valuable sort of goal to strive for, sort of making your research reproducible, which is why I'm excited to teach this to upper level undergrads and beginning grad students, because to sort of inform and inspire the sort of next wave of students that will be potentially entering academia to do reproducible research is sort of very important in my mind. And so if we scroll down the syllabus, we'll think about what skills that I would like you to learn, or that I'm trying to impart during this course. And so I will teach many computational tools. I don't want it to be an entirely methods or tools driven course, but also I'm kind of okay if it becomes that, because I think the tools are really important, and hopefully students continue to use these tools after the course is done. And so sort of my hope is that over the course, as you can see on the syllabus, it is expected that students sort of gain knowledge about what is open science, and then more specifically, what does it mean to make research reproducible, as well as actionable things like how to make research reproducible. And along those lines, I'll be teaching tools, including Git and Bash, so shell scripting a little bit of, mainly focusing on R as a statistical programming language. But I'll also be teaching continuous integration using Travis, and many other computational tools, even as far as containerization using Docker, if there's time and interest. I imagine the course will sort of change. This is my first time teaching the course. And so I imagine the course will adapt with student interest and ability. So yeah, then that follows the next one. The syllabus is absolutely subject to change. Hopefully these lectures will be compartmentalized enough where even if the syllabus does change, that I can sort of tag it with like, learn Git, and it'll make sense. And people outside of the course and inside the course will be able to follow it effectively. That's the goal. So before I go any farther, I guess it seems prudent to sort of think about where I'm coming from. And so you know that I'm a new professor in biological sciences at LSU, but you don't really know why I care about reproducibility in scientific research. And I think why I care is because, so the first experiment that I ever did, I worked at University of Georgia as a PhD student working on daphnia and a parasitic disease of daphnia as a model system to test epidemiological and community ecological theory. So daphnia are these small aquatic crustaceans, really tiny. And I ran an experiment which I thought I had so much replication, right? And so this is one thing of a model system is I have the ability to replicate it many, many times. And so I had like 20 populations per treatment level or more. And I found one thing, and the results were sort of a little bit confusing there. And so it didn't take too long to run again. And so I thought, I'm just going to reproduce it. I'm just going to replicate. So not reproduce, but just replicate. Just taking the same methods. I'm going to go through the experimental protocol and repeat all of the steps. So it's a fundamental difference between reproducibility and replicability. And I found something different the second time that I did it. And that wasn't really, that didn't really make me that stoked about science at the time. And so, and then as I went on, I think by my second or third year, I started seeing people release code and release data that were openly available. And it seemed like the best way to move science forward and to sort of bypass some of like coding errors, data entry errors, things like that. Like let the community be able to catch that, and we can all collectively and collaboratively build on science. And so that early in the PhD, I had an experience with replicability. And then as I progressed further, I became more introduced in actual reproducibility. And so I think starting maybe second or third year of my PhD, I started releasing all of my coding data on Figshare, which Figshare, if you don't know about it, is a fantastic site and sponsor this video. I'm just kidding, they're not the sponsor of this video, nobody's sponsoring this video. I guess LSU is indirectly sponsoring this video. So thank you, LSU. But Figshare is fantastic, and I recommend you check that out as a way to sort of release coding data. Also around that time, I had been getting more involved in open access and open science. So I started to publish more in open access journals. I started to think about the sort of shift in the current publishing model, which I won't go into detail because that's sort of to the side of reproducible research. But also accessibility to data. And so I started to use existing open source code through either other people's code, through like Figshare or GitHub, as well as through R packages to analyze existing data streams that were not my own. So that were found data from repositories like Data Dryad or Figshare, etc. And I sort of gained a sort of fundamental appreciation for the willingness of researchers to be open, to treat science as a public good. Like we, as scientists, I guess speaking to some, are funded by the public. We're funded by tax dollars, so we don't own the data, and we should probably stop acting like we do. And so any way to advance science faster and more efficiently is sort of fundamentally better. That's especially true now during the COVID pandemic, as data streams that are flowing are used to build epidemiological models and inform policy decisions. And so keeping those data open is actually incredibly important. And keeping those analyses reproducible is tantamount in its importance to keeping those data streams open. And with that, I will now get off my soapbox and sort of continue on. There'll be a lot of this, by the way. This is me as a lecturer. I am a little bit maybe scattered. And so, yeah, I guess I apologize, but I don't apologize. I'm sure I'll get better as a lecturer in the future, but now, I mean, this is my home, and this is a random intro YouTube video, so, oops. To go over sort of specific things for LSU students, as we see here on the left, there's information on grading. And so overall, we'll have 5 assignments that are each worth 50 points. These assignments will be submitted through the use of GitHub Classroom. And so basically your assignment, and this is not actually just for LSU students because other people can submit assignments. They're automatically graded using Travis CI for the most part. Some assignments just can't fundamentally be graded using continuous integration. However, most of them can and most of them will. The syllabus will also change, and so here we see that I sort of separated it out to cater to both undergraduate and graduate students, thinking that it would be dual listed as a 4800 or a 7800. It is only listed as a 4800, however, graduate students can take this course and still receive credit. Also, as of now, the only people who have signed up for this course happen to be graduate students, and so I am teaching at the level that I think is most beneficial to them in terms of where their science is at. And so I reduce the amount of assignments and busy work, and I'm really trying to focus on teaching the tools and teaching and gearing it toward that final product. And so the final product is a project that you will hopefully start and bring your own existing data and analyze it in a reproducible way. So if you hand me a final product, I can run it on any machine. Sort of independent of operating system and dependencies and all of the sort of garbage that we run into. And so, yeah, proprietary data access. So if you hand me MATLAB code, I won't be that happy because I don't have MATLAB because it's a proprietary software. Attendance and participation, that will mainly, or obviously be only for LSU students, and that will be participation in the paper discussions and the Zoom calls. I have no way of knowing if you are, as an LSU student, viewing this word vomit that I'm calling a lecture. So hopefully you are, because I think you can learn a lot out of it, but I have no way of knowing. And then the final project will be sort of the bulk of the points, sort of that and assignments. And then the final exam will cover mainly higher level concepts of reproducibility with maybe some small sort of coding bits, but only like conceptual coding. I'm not going to say, write this R code to solve this problem. I think that's unnecessary. And so we scroll by. I recommend you read these as LSU students, but I won't go into them now. And so it just focuses on specifics about the project, specifics about attendance, and specifics about the assignments, which hopefully by the time that class starts, I will have all of the assignments basically ready to go. So people can proceed at their own pace, essentially. A clear academic honesty and disability services statement. Yeah, feel free to reach out. These are all hyperlinks, and so reach out to them. Hopefully, YouTube's captioning will work. I'm trying to speak very clearly, so hopefully anybody sort of that would require closed captioning has it, and if not, man, please send me an email and I'll try to find a better platform than YouTube to get closed captioning, or I can close captioning myself, or I think we have services at LSU that might do that for us. So to go over the schedule a little bit, this is week 1. It's just all background. So it's just me pontificating and talking. Starting next week, we're going to get into the fun stuff. And so next week's lecture will cover Git as a version control language, its association to GitHub, the structure of GitHub in terms of the GUI and how to interface with it, as well as the Unix command line. And so There are many GUIs GUI stands for graphical user interface, to submit things to GitHub, and so to interface to our local machine with the cloud. But I sort of recommend, and I plan to teach a command line approach. And so the command line is the thing that gives you sort of all control over your computer. And then we'll go on and go over sort of the basics of R, Markdown. I think we'll talk a little bit about the tech, but I'm not even sure I want to cover that, even though it's a lovely typesetting language. And then we'll get a little bit into what is called dependency hell and how to get out of dependency hell, and then talk about parallel computing. And the final 2 weeks will be maybe some spillover in terms of things that I just didn't cover in enough detail, or we'll just focus on presenting the final products, which I'm really excited to see, and I think it'll be really cool. I also listed some things that are not covered in the course, but I could potentially cover in those final weeks, those final couple weeks, and that's creating and structuring an R package. And so I'm author or co-author on, I think, 3 or 4 R packages currently, 2 of which are sort of my own that I maintain and that I'm all about. They're good stuff. Code benchmarking, and so I don't really go over line profiling too heavily or benchmarking to write efficient code. And so basically trying to make your code as efficient in terms of computational resources and time as you can. And then lastly, and I thought it would only be of interest to sort of a niche crowd, would be the handling of spatial data in R. And so trying to basically replace geographical information systems, or GIS, with R alternatives, so things that are more programmatic. Because GIS can sometimes be programmatic through the underwriting of, like, I think it's Python code a lot of the time, but a lot of it's point and click, which is not ideal, in my experience. This bit's but just more specifics for grad students. And with that, I think we've completed the rundown of the syllabus. And so we can move into the rest of the sort of lecture, which is Markdown as a markup language. So I'll close that out. And so now we're back to the lecture on the left, on the Emacs screen, and on the right, we have the compiled PDF. And so it gives the reading for the week. We go over sort of my expectations for people who are taking the class, which I won't go over here. Feel free to read them in your own time. In the second lecture, when we're live and I'm able to talk to people in the class, we're going to go over your expectations of me as a lecturer and what you want to get out of the course. We already went over a bit on the difference between reproducibility and replicability, and why do reproducible research. And I think a lot of people who enrolled in this course just saw R. They recognized, like, graduate students at this point in time need to know a statistical programming language, period. Yeah, I remember I was a postdoc at University of Helsinki, and in a conversation with a big group of people, I essentially said, at this point on, I think all ecologists need to, in some part, be computational ecologists. And people took that in an odd way, and they said, oh, you don't want to be I'm a boots on the ground ecologist. I'm a boots on the ground scientist. I'm a muddy boots scientist. And that wasn't what I was trying to say at all. I think what I was trying to say is, cool, like, collect the data. Collecting data will always be immensely needed, right? In order to understand a natural system or any system, we need to have data. However, anybody getting a PhD or master's degree now also needs to be able to analyze that data effectively. And in order to do that, it's getting increasingly difficult to do that using these more simplistic or point and click tools. And it's more important that students learn how to process data programmatically through a language like R or Julia or Python or MATLAB, one of the others. Yeah, so here I go over a little bit about open science, which we've sort of already covered, and hopefully I've been sort of clear about that and not pontificated too much. And now I'll go into a little bit of logistics. And so what I use in my tool chain, which I will try not to be too prescriptive about. And so I recognize that people coming and watching this YouTube video are watching it on different operating systems. So from my screen, it may look foreign to a lot of people. I'm using Ubuntu, which is a Linux operating system. And then on top of that, I'm using a Windows manager called Awesome. The Linux operating system is fantastic. I've been using some flavor of Linux for the past, oh man, I don't know. I'm gonna just age myself here. It's something like 12 or 15 years. And so it's been a long time that I've been sort of involved in using it. And I'm a huge fan. So I would encourage you to try out Linux operating system if you feel the sort of desire. There's two clear ways you can do this. So first, there is using a virtual machine. And so Ubuntu, you can just Google search Ubuntu. You can download the ISO file, which is the operating system. And then you can download a virtual machine software like VMware or VirtualBox, which I think both of those are free. They might even be like subsets. Is VMware like a company? I don't know. I'm not an expert in VMs, sorry. And you can run an actual operating system contained within your own operating system, if that makes sense. So think of like this screen, this window here is an Emacs screen. That window in a VM would correspond to maybe an entire other operating system. The second option for using Ubuntu or Linux operating system, I mean specifically Ubuntu, for people enrolled in the course is, if the video is going through, if not, I'm just holding a flash drive to myself, is I've made a bunch of persistent Linux operating systems on USB. You're free to take one. I'll make them available to students in the class. What this does is you plug this USB into your computer when it's shut down. You start it up and enter BIOS using, typically it's like F2 or F10 or 12. It's one of the function keys. You can Google that one. I should know that. Enter BIOS, and then you can boot from a USB drive. You can do this with on-campus computers as well, if you're using a campus computer or your personal computer. And then you will basically be able to run a persistent, which means you can save files and they stay on the drive, a persistent Linux operating system from a USB. The benefits that I see in the Linux operating system is it will come if you take a USB, or it can easily have access to tools that are really, really useful to reproducible research that may not be there if you're running Windows or Mac. And I said I've been running Linux for so long that I may not be a great resource in terms of helping troubleshoot, download, and installation issues for some of the tools that I want to teach in this course. I will try my best, but like, I really don't want us to get hung up on installation issues and version issues, because that would be sort of an embarrassing stumble block for a course on reproducible research. And so things that sort of come either natively or easy to install within the Linux operating system, and specifically Ubuntu, which is very user-friendly, are the bash shell. And so we're going to go over shell scripting. However, that is now available on it's now available on Windows operating systems. And so hopefully this link still works that I'm highlighting down here. If you're a Windows user, Windows 10 and above, you should be able to get the bash shell and have a Linux subsystem to your Windows machine. And then if you're running Mac OS, it comes with the bash shell. So that should be fine. You should be fine there. Things like make, and so that is a GNU product. We will go over how to use make files. I think they're incredibly useful, even for small scale analyses. So I use make files to compile this lecture, even though it's simply a couple of shell commands. I think they're really useful, and I will go over their structure, as well as Git. And so if you're running Windows, you download Git, and you get this whole like Git bash as a separate thing, which is not really ideal, because if you want to make other bash commands, you can't necessarily do that when you're in Git bash. And then lastly, R, which is agnostic to operating system, which is fantastic. Basically use this as a list of things that you need to start to get downloaded and start to just get installed on your machine if possible. If you want the USB that is persistent Linux drive, let me know, and I'm more than happy to sort of show you how to use that. It's hard to do a video on how to use that, and so and especially doing a Zoom call as well, it'll be difficult. So there's some things that we're just missing from face-to-face lectures. I think that's all I wanted to cover there. And so there is some operating system issues that may come about. However, we'll get around them. With regards to R, you can use, so R as a language has its own GUI that you can use. You can also just write R code in any text editor. So I'm using Emacs here just for simplicity. You can use any text editor that you wish. And then just copy commands over to the bash command line. And so here I'll open command line, and you can see this is my bash terminal. It gives my username, tab, @ and then it's the computer ID. I've named my computer Serenity. And if I hit R, it enters R. And so now I can type in R commands. Like I can just randomly set A as a vector of 1 through 10 and go from there. So you could also do that, and then you easily have access to other things as well, to your underlying computer structure. Okay. So I think that covers all the logistics of the course. It covers syllabus, covers what I'm hoping that you get out of this course in terms of tool sets. And now we'll actually go into a short tutorial on Markdown. And why I'm doing this is because 2 tutorials from now, I'm going to teach you R Markdown. And that is basically just R mashed into Markdown, if you can view it like that. And I'll go into more detail on that later. Additionally, as I mentioned before, Markdown is used as a markup language in many applications online. So GitHub uses their own flavor of Markdown, which will accept all of the syntax that I will go over. This lecture itself is written in Markdown. And so this is the actual code that I'm scrolling through now. And it's written in Markdown, and when it compiles using Pandoc, which is a fantastic tool chain from command line to convert files to other forms of files, essentially. And so this Markdown becomes PDF, and it becomes well-rendered PDF, right? And so this looks very professional. Big fan. And so we'll go over a little bit like the structure of Markdown, and Markdown in particular because it's really easy in that it reads basically like plain text. And so if you've been following along with the sort of interplay between the left and the right panels here, you'll see that it looks really similar. So I'll scroll down and we see what is Markdown, and then right there, what is Markdown? Very, very sort of simple in its structure. And so what is Markdown is that it's incredibly lightweight markup language that you can use for formatting. many things. And so you can write, you can write websites in Markdown, theses, you can write anything pretty much in Markdown. What's nice about it is that it's pretty much just plain text, right? And so it's sort of independent of operating system, putatively, as long as you have access to something like Pandoc, or not even something like, but Pandoc, which controls your ability to compile to HTML or PDF. In its simplicity, I think Markdown is actually relatively future-proof, which I put in quotes. And the idea where is like things like certain database formats, old like Microsoft Works documents, like things like old Fortran code. That's probably still runnable, but many things in that same vein are just fundamentally not runnable and not even openable, right? And so if I tried to open something like that in a text editor, it would just fail or give me gibberish. Markdown is basically plain text with very little additional syntax. So I think that's a sort of clear benefit of it. And now we'll go over a little bit of the syntax. Excuse me. And so first, we'll go over headers. Headers are just identified using, if I can just highlight one of them, pound signs. And so if you have one pound sign, it is the highest level header. If you have two, it's subheader of that. And so think of it as section, subsection, subsection, paragraph, and so on. I think it goes to either 4 or 5 different headings or nested subsections. This also shows on the left, sorry, I'll scroll down so we have this. This also shows on the left the utility of code blocks. And so here I'm using 3 backticks to identify a block of code. And what that tells Markdown is to show that as code. And so this is Markdown syntax, right? And so hypothetically, this should correspond to different levels of headers. It doesn't because it's nested within that code block. And so that code block says, treat this verbatim, treat this as code. And so we see on the right that it's rendered in sort of a monospace font, and it's rendered as what it says, not what, quote, it means in Markdown language. Then I have it outside of those block quotes, outside of, excuse me, the 3 backtick code block, and it renders differently. It renders treating them as headings. So that's a utility that's right there, especially when we start to get into R, because these three backticks to set up code environments, it's not just for R, right? You can set up bash scripting, you can set up Python highlighting and scripting. You have a lot of different backends that you can work from. Scroll down. In terms of actual text, like let's say I just wanted to type a paragraph of text, it's very, very simple. You just type a paragraph of text. So text handles as text. Seems intuitive. However, when you want to do styling on that text, and so your overall document that compiles to HTML or PDF, you may want a specific code highlighter. You may want a specific margin, right? And to do that, or specify title or date or any one of these things. To do that, you will need to use what's called a YAML header. YAML stands for yet another markup language, and so you're basically using 2 markup languages, one being Markdown and the other being YAML. YAML is useful, and I hate it. It's useful to a point. It can be a little bit annoying, and we will hopefully not get into the annoyance of it. Basically, it's very sensitive to spaces, and I don't like languages that are sensitive to spaces. And so your YAML in your Markdown document sits at the top of the document. It's the first lines that will be identified in your Markdown document. It's separated into a block of 3 dashes. So I'm highlighting it there on the left screen. This is a very simple example of a YAML header. You can do a lot with YAML headers. This one is just what I used for this lecture, and it tells you all that you need to know, basically. So it tells you the title of the lecture. So I'll scroll up and we can see, oh, it's actually not, it's the title of the other. It's the title of a future lecture, actually. I don't know why I copied that one over. So that'll be in like 2 weeks. This is the YAML header of a lecture from 2 weeks from now. And the author, me, the date, I left blank, I didn't want to fill in a date. And then I think more importantly, or maybe most importantly, is the output format. So this could be an HTML document, in which case you would just simply change this to HTML document, which is the default, which is nice because HTML is not going anywhere. Like, you can run HTML, render it, and everyone will recognize it. But I typically output to PDF, which is portable document format. And there are other outputs that it can have. Those are the two sort of most obvious and clearest and most often used ones. So now we'll scroll down. Let's say you want to, let's say you want to incorporate things that you wouldn't in Word, where you hit Control B or Control I and you switch into bold font or italic font. You can't really do that here, right? Because you can write this code, this markup language, in any text editor. And so it's going to be agnostic to weird formatting like that, which is actually a strength of Markdown and other markup languages. So here instead, for italics, you're going to use an underscore character. I will highlight it there, just the underscore, before and after the body of text that you want to make italics. The same with bold text. And so when you want to identify bold text, you'll have 2 star characters on either side of whatever you want to be bold. Block quotes are sometimes useful. And I'll go over how they work really quickly. And it's very easy, actually. You just add this greater than operator. And so here we see the utility of the code block again, where I'm entering that environment with 3 backticks, and I'm ending that environment with 3 backticks. And what that translates to is it just shows the actual markup language in the PDF document. When I put that outside of this code environment, with that outside of those 3 backtick blocks, it actually renders in the PDF as it should, as an indented block quote. And the quote is from Slaughterhouse-5, and it is, "Everything is beautiful and nothing hurt." Okay, and now we can go into lists. And so enumerated lists are those that you go sequentially from 1, 2, 3 to n to onward. And those are very simple. You just would write them as 1 followed by a period. I think it also works if you use a parenthesis. And so in this code block, I enter this environment, I write break an egg as the first way to prepare a breakfast if you're not vegan, and then make an omelet if you feel like making an omelet. Step 3, eat the omelet if you feel like eating the omelet. And here that becomes sort of code block, and then outside of that code block, it actually renders to a slightly indented enumerated list. If you don't want your list to be enumerated, you don't want it to be 1, 2, 3 to n, you just want it to be itemized, so point. It's very simple, and you can use any one of these 3, and there's probably more, different delineators. And so the plus sign, the minus sign or dash, however you want to see it, or the star all work. And so in this code block, I provide random breakfast items that you might find here in the American South. Eggs, grits, and cheese. And when they're identified in the code block, it shows each one of those delineators. And so you see the plus sign, you see the star, you see the dash or the minus sign. But when you actually render that, it all becomes the same itemized list with a point identifying the item in the list. Hyperlinks can be added, which are really helpful to link to code repositories or to help pages or to whatever you want, your website, your email, anything that would require a hyperlink. And so the structure of it is a square bracket with some descriptor within that square bracket, and then followed by no space, and it's just parentheses, and within those parentheses providing the actual web address or URL. I give an example of here. If you haven't already downloaded R on your machine and want to, this will put the text, click here, and that link will go to the R project. And so on the rendered PDF, you can see none of this is hyperlinked, and then when I go over here, it's hyperlinked. And so when I scroll over, it says that it's going to go to https:// R project. So we can click on that, and it's opening up in a window that you can't even see. So I'm just going to close that. And then I talk about hyperlinks and images in the same breath because they're really, really similar. And so this compiled PDF is actually incorrect, so ignore that and look only to the syntax of the Markdown syntax. So I haven't compiled this in a while. This is a good example that sort of, it's sometimes a little bit of a disconnect in students' brains where, because they're used to, you open up a Word document, you edit it, you save it, and it's done, it's one thing. This is not just one thing. This is code to produce a document. And so this code on the left panel has to be compiled to create the thing on the right panel. And so this on the left panel is actually more recent, as an error on my part before recording this lecture, than the PDF on the right. Teachable moment caused by my own incompetence. And so how you actually embed an image in Markdown syntax is to basically do a hyperlink, but precede it by an exclamation point. And so here we see the same syntax that we would use for a hyperlink. So you see square brackets, you see the caption information, and then you see open parentheses, the actual path to the image, either a web path or a legitimate, or not legitimate, a local path to something on your machine that can then run and be compiled. And so an example of this is provided here, where I'm going to have a cat that is my figure 1, and it links to a JPEG image, which is in this repository. And so here I link it with the text, the caption cat, and you can see it renders and says figure 1 cat. And then it links to the image and portrays the image in the compiled PDF, which is an image of a cat. Pretty clear, good stuff. And then finally, which is something that we've sort of gone over throughout, and I think I want to end here because this is one of the strengths, and this is why I've been droning on about Markdown, is its ability to incorporate code directly into it. And so we've talked about the coding blocks as basically verbatim, and so we can see things like this. You can see what you actually type instead of having Markdown interpret what you type. Our Markdown, which I will be using starting either next lecture or the lecture after that, goes a step further. And it actually runs the code in R. And so what that means is that you can have code and text living in the same document. which means you can have, instead of just having a big long R script, despite it being well documented, it's always a slog to go through. And so this means that you could actually write prose. You can say, here we develop this model, and these are the parameters, and this is the reference to the model. And then you can actually provide the code directly in that file. And many people do this. Many people actually write manuscripts, entire manuscripts in our Markdown. And how you do that is just like that. You just specify in the code block on the left there that that is our code. And so here, and if this file was named .rmd, which it's not, it's named .md. And we'll go over how to compile our Markdown documents. I won't go over how to compile Markdown documents because it's needless. You won't ever be writing just a Markdown document. But let me know if you would like to know how, and I can show you. Or you can look on Stack Overflow, and I'm sure there's tons of resources. And so here, this is a block of our code that basically assigns the value 1 to the variable y, and then outputs y, or should print y to screen. All right, and I think that gets us through the entire first lecture. So stoked that you stayed with me. I hope this was clear. In future tutorials, we'll go over more methods-driven things. Please let me know if you would like me to change something in my lecture style. I switched to Emacs mainly because I was eventually going to increase the size of the text if you couldn't read it easily, or also because my normal editor uses like a dark mode, and it's needlessly complicated looking, and this is a little bit more straightforward looking, I think, to many people. Because yeah, the last thing I want to do is make people feel like they can't understand these concepts, or that they have to be using what I'm using in order to fully do reproducible research. Because you can do reproducible research on a Mac, you can do it on a Windows operating system, you can pretty much do it on anything, not quite. And so I want this course to be open and inclusive to all different people with different backgrounds and operating systems and coding abilities. And I'm confident that we can get there, and I'm excited to continue teaching this course of my own design for the first time. So it's going to be an experience for both of us, for all of us collectively, but thank you for staying with me. So I'm going to stop screen share. And now we switch back to just the Zoom view. Thanks for staying with me. And I will see you in the next lecture, which I believe will go over Git, GitHub, and something else. Bash scripting. We'll go over the shell, Git, and GitHub in the next lecture, which will be about 40 to 45 minutes. And hopefully that's what this one is, but I have no way of knowing. I think maybe it's a little bit shorter than that. I don't know. And we'll see if I get fancy with any video editing software or anything, or if I just give it to you like this. So thank you for watching. Take care.